There are some integrals that just don't look like integration by parts, but it turns out it's exactly the right thing to do. And actually, once we do it for one, we realize, wow, maybe it's something I should be looking out for every time. Anyway, natural log of x. Natural log of x, I can take the derivative. It's 1 over x. But the antiderivative? Well, let's do this by parts. Initially, it doesn't look like a by parts problem because it doesn't look like the product of two things. There's just one thing there. There's just the log x. But actually, there's two things. There's the log x and there's the dx. So I'm going to put log x in one of these two places, either the u or the dv. I'm going to put the dx in the other place. Well, it doesn't make any sense to put the dx with the u, so the dx has to go down there. But I might just put a 1 here for u and put log x dx down there. The problem is if I put the log x dx down there, I have to integrate it to figure out what v is, and I don't know how to integrate. That's my problem. So I'll put the natural log x right here, and I'll just put the dx down there. The thing is, I can take the derivative of log x, so I'll do that. It's 1 over x. And I can take the integral of dx, which is just x. So according to integration by parts now, I started off with u dv, so now I get u times v, so x times log x, minus the integral of v du, so x times 1 over x. Oops, there should be a dx right there, because that's a differential. But x times 1 over x, that's just a 1. And I could do the integral of 1. What's the integral of natural log of x? It's x ln x minus x plus a constant, done by parts. Again, it doesn't jump out at me that that should be by parts because there's only one thing. There's not a product of two things. But it works. And actually, there's a couple of things that come out of it. One is that I may look at integration by parts in a lot of situations, but also I just want to look at the natural log when in integration by parts. If I had something like this one, for instance, if I had the integral of x to the 7th times the natural log of x dx, right? My initial reaction is, oh, this is going to be like, you know, a polynomial times an exponential or polynomial times a trig, where you're going to make this be the u. So u du v dv. And the thing is, you got to put the log x down here if you're going to put the x to the 7th there. It's like, I don't want to put the log x down there because it's a pain in the neck to integrate. We just did it, right? But so I'd rather put it here. So that means the x to the 7th goes down here in the dv, and it's like, oh, that's going to get more complicated. But it turns out that it gets more complicated in a way that's compensated by this, because the derivative of the natural log of x is 1 over x, so the differential is 1 over x dx. And if you integrate this thing, you get x to the 8th over 8. Normally, I would put the polynomial here, except when log x is there, I like putting that in because I don't like integrating log x. So u times v, x to the 8 over 8 times the natural log of x, minus the integral of v du. Well, v here is x to the 8 over 8, and du is 1 over x dx. And wow, that actually is nice. One of the x's cancels out. So I just got x to the 7 over 8 times dx, which I can integrate that. That's going to be, what just happened? Stop. X to the 8 over 8 ln x minus, what's that, x to the 8 over 64 now, plus a constant. Okay. In general, I would put polynomials as u and the other thing as the dv, but in the case where it's hard to integrate that thing, then it goes here instead. And this one's okay to integrate. And then, hey, we luck out and they cancel. They kind of combine it to be something that we can integrate. this is just the idea now. It leads to a lot of things. I can integrate all sorts of stuff. How about the integral of the inverse sine? How about arc sine of x dx? In Calc 1, I learned how to take the derivative of arc sine, but I never learned how to integrate it. So let's see if we can use that. I'm going to put the arc sine right here. Actually, I'm going to write it this way. Sine to the minus 1 of x. That's not cosecant, right? This is the arc sine. This is the inverse sine function. And put the dx down there. The derivative of the arc sine is 1 over the square root of 1 minus x squared dx. And the antiderivative of dx is x. So, integration by parts, u times v, x sine inverse of x minus the integral of v du, x over the square root of 1 minus x squared dx. And that one, can I do that integral? Yeah, I think I can do a u substitution. Let me let u equal the stuff inside the square root there. So 1 minus x squared. Then du is minus 2x dx. Actually, I've got the minus, but it's outside. Let's pull that inside and make that a plus. But then I need a 2, so put a half out in front. So this is x sine inverse x plus a half times the integral. This is a u square root on the bottom. So that would be a u to the minus a half power times, the minus 2x dx is the du. So good. That now integrates to is 1/2 u to the plus a half divided by plus a half, so that would be times 2 plus c. So the half and the 2 cancel out. I've got x sine inverse x plus u to the half power, but u, remember, was 1 minus x squared. So raise it to the half power. That's the same as taking the square root. And we've got that integrated. Because I know how to take the derivative of the inverse sine, I can use integration by parts, and it turns out I can find the antiderivative of the inverse sine. I can do this with so many things that I already know how to integrate, but I just want to do it anyway. It's just like, hey, let me try this. Let's see if I can. Let's see if I can do the integral of x to the n. You may think you know how to do this. I hope you're right. But I'm going to do it by parts. I'm going to let u, du, v, dv. Let's just put the x to the n right here because I know how to take the derivative of it from Calc 1. Let's put the dx over there. This is nx to the n minus 1 power. And this is just x. So this would be equal to u times v. So x to the n times x minus the integral of v du. So nx to the n minus 1. Whoops, that had a dx in it. And then it's times another x there. I have everything there. This stuff. Yeah. Okay, well, this looks like x to the n plus 1 minus n times the integral of x to the n. Heck, I started with the integral of x to the n, and I'm back to it. Hey, I think we've been here before. All right, let me take this, subtract it over the other side. I got the integral of n x to the n dx equals x to the n plus 1. Whoops, I'm going to add this over the other side. So I've got plus n times the integral of x to the n dx equals x to the n plus 1. And then those get together to be n plus 1 times this integral equals x to the n plus 1. And then I'm going to divide. So the integral of x to the n dx is x to the n plus 1 divided by n plus 1. And there's probably a plus a constant that got lost somewhere. And sure enough, this is exactly what we expected. but it's nice to see that you can do it other ways. One of the things I hated about Calc 2 when I was a student was I felt like they were just giving me a bunch of rules that you had to recognize. Oh, this is a place where you do U substitutions. Oh, this is a place where you do integration by parts. Oh, this is a place where you do all these other things I'm going to teach you over the next couple of weeks. Um, where now I don't see it that way. Now I see it as you've got some tools. You've got the notion of a U substitution. You can try it anytime you want. If it works, great. If it doesn't, well, try something else. Maybe a different U substitution or try parts. Parts, generally, you're using integration by parts when you got a product of a couple of things that don't go together so well. But actually, you can use integration by parts anytime you want. You can always just let u be the thing you've got and the dv be dx and see what happens. So rather than taking the integral of what you had, you're taking the derivative, and then you got to integrate what's left. Don't be afraid to make mistakes. Don't be afraid to try something and have it not work. Try something else. See what happens. Eventually you find something that works. With practice, you're more likely to get things to work the first time. But anyway, integration by parts, it's a powerful tool.